spatial context of individuals. Okay, so I'll start this up here. We're going to be talking about how AnyLogic offers spatial embedding in two-dimensional landscapes. AnyLogic has a very sophisticated three-dimensional representation as well, which we won't be going into. We'll be taking a look at two different ways in which AnyLogic represents space, one discrete, one continuous, and look at how mobility can be accomplished within these spaces. So spatial embedding is very interesting. It's a variety of areas cutting across areas of interest and help. Sometimes it can be used to express in potential dynamics for certain types of problems. Aspects of locality of influence and transmission often occur between co-located individuals. There are certain types of phenomena, such as spatial concentrations of pollutants, think smog or water pollution, etc., which distinctly is spatially rooted. Many researchers also have an interest in combining these spatial models with GIS data, so data on spatial availability of resources, on routing from one place to another, and obviously spatial concerns, spatially geographic concerns of core interest in this area. For these reasons, AnyLogic provides quite a lot of support for spatial reasoning and dynamics. And there's two fundamental ways in which it represents space. This is one of the more important sort of distinctions to have in mind when you're working with AnyLogic models. One is a form of continuous spatial embedding. The idea here is that we depict the space. Agents are assumed to be very small in relation to that space. We don't really have to worry about mutual exclusion. Agents can move past each other. They can interact, of course, but there's no rule that they can't see atop each other or something like that. Think about viewing Los Angeles from space. Essentially, people are so small that you don't really worry whether their paths cross, whether they're going to block each other, or what have you. We've seen actually aspects of spatial embedding in a continuous sense in some of our example models to this point. The other sort of type of model that AnyLogic supports is one where we have discrete space. The space is broken up into a set of cells. And there's mutual exclusion going on here in the sense that a cell can be empty or it can have exactly one agent in it, and not more than that. So we can have perhaps a house or a store in this lot, or the lot can be empty, here's a brownfield, but it's only one thing can go in there at a time. And in this situation, the space is divided into columns and rows, discretized, quantized, it's broken up in a gridded fashion. Whereas in the first of these, it's as fine-grained as you want it to be spatial. It seems to be located, at 71 exactly, 71.00001, and however in their x-coordinate, however level of detail required spatially, you can accomplish it in the first of these. The second of these is divided into these cells, these grid squares. Now, there's an environment maintained in AnyLogic agents. In AnyLogic 7, this is maintained associated with the agent. We've actually seen that already. I'm going to switch to that here so we can have an idea of what I mean by that. But for example, when we have I'll load in one of the models that we built yesterday. Say this model associated with the open population. This is this model which incorporated factors associated with immigration and so on.
we scroll down in main, you may remember this area where we set the layout type and the network type. There was also an indication here, what's the space type? Do we have a GIS integrated space? Is it a discrete space or is it continuous space? Okay? We've been operating thus far in continuous spaces. These people, when we ran this yesterday, what we saw is these people were located in space to whatever degree of fine-grained accuracy needed for our model. And today we're going to be looking at both types of spaces. Okay, so fundamentally agents, the surrounding agent, in this case main, maintains this environment, and we can specify whether it's continuous or discrete. If it's discrete, what are the neighborhoods? Do you have neighbors only north, south, east, and west, or in 8 direction? Okay, so moving on here, within continuous space, we have people, moving over, or situated in a fixed way over some area, and we've connected people together, for example, if they lie within a certain distance. Within a discrete space, we have rows and columns specified, and for some reason the coloration of this is off, and I apologize for that. For some reason this is turned non-transparent. Let me make this transparent. It'll be much clearer what's going on here. So here, with a continuous space, we specify the width and height of the space. With a discrete space, on the other hand, we specify not just the width and the height, but also the number of rows and the number of columns. Okay, and that again is associated with dividing the space up into squares. Okay, I would note that we have seen an aspect of both of these types within the past few days. So the open population model, as well as most of them, have been continuous. For discrete examples, we could go to that very first model that we saw, this agent-based model that we had loaded in from the example models. And we'll see there that individuals were laid out in a grid, and those individuals were interacting with their neighbors north, south, east, and west. Oh, do I already have it open? I already have it open here. So if we go to that very first model, and we scroll down here, we'll find that it's a discrete space, so there are these cells. And that's what allowed us to see when we ran this model, allowed us to see sort of the space of cells packed next to one another. These are cells in space. Oh, wow, look at that. Oh, man. I must have changed something. Okay. In any event, the deal is we have these cells in space in this regular grid. So you can specify both. My original hope was to show, to build up an example model for both. It's quite easy to do. Because of space constraints, unless there's a lot of interest, I think I could find my attention to the continuous space. If there is interest in the discrete space, it would add about 45 minutes, and we could do a little example with that too. But we'd have to do it after lunch. So I'll wait and see how things go with this first one. Okay, so folks, I'd like to add a continuous space model, and we're going to use it to incorporate not only aspects of spatial embedding, but a separate but related issue of mobility. Okay, and that brings me to the second major topic we're going to be finishing with this morning, which is people's movement in space. Okay, so we talked just now about spatial embedding, and I noted the two types of embedding here. Okay, we're going to be talking about mobility now, mobility within these spaces, so people's movement. And there's two types of mobility supported by any logic matching up each of these types of embedding. So for continuous mobility, people move in a certain direction. They sail across the space in a smooth sort of way with some velocity, and they go in a certain direction. In discrete space, they move to to another cell. They hop to another cell. A cell next to them or a cell across the space. Similarly, they can hop actually in contiguous space to another location, but it's a little bit more common for them to move slowly, to move in a sort of continual way. And there's a set of ways in which we move people. One of the most basic is by calling move to on someone. You could set their velocity, you can set their X and Y location, you can jump them to a certain location. You can also get their X and Y location, ask them if they're moving, ask them where they're moving, and set their rotation. So I think what we'll do is we'll build up a little model here that I've chosen to shed light on some of the project needs, okay? This is going to shed light on the different environments to which people are exposed in the course of the day. So, to do this, I'd like you to create a new model. I think this is familiar to most of you. You do File, New, Model. And why don't we call this Simple Institutional Mobility? Well, maybe we'll just call it Simple Mobility. Simple Continuous Mobility. That's better. Simple Continuous Mobility. Sorry, folks. Simple Continuous Mobility. Okay? So we're adding this model. And as normal, this is the first model of the day you built, so maybe this is a bit rusty, but let's rehearse the basics. Okay, so, ladies and gentlemen, we wish to add people to this model. How do we do that? Anyone remind me? Okay, right click there and do agent type, new agent type. We're going to add a person. Okay? So we're adding a person to this model. So we did that we just created this new model, and then we right-clicked on the model, and we did new and agent type person, right? Okay, now let's go give this person an appearance. How are we going to do that? Okay, let's go give them a picture. Let's go give them let's go make them appear like a little person. How do I do that? Okay, yeah, we go down to pictures, that's right, and we drag in person here, okay? Okay, good. Okay, next, we want to give them a sex. Okay, we'll do that, excuse me, I misspoke. We want to give them an age in this case, okay? So how are we going to give them age? We add a parameter. Good. Okay, so we go to palette, go to general, and we drag in a parameter. We're going to call it age. Now, in general, ladies and gentlemen, age is going to be, in some models it's going to be a parameter, in some models it's going to be an aspect of state. Sometimes actually it's going to be changing. In this case, we're going to assume the time frame of the model is small enough that we don't need people to age. I'd be glad to show you aging in a separate context, but just to sort of simplify this discussion, I think we'll treat it like a, oh man, I could do aging in about 3 minutes. How many people want to see aging here? Continuous aging. Okay, we're going to do continuous aging. Sorry. Okay. Okay, this is what we're going to do. You want to do continuous aging? We just dragged in a parameter. Instead of being called age, it's going to be called birth date. Okay? It's going to be called birth date instead of age. Okay. Great. Now, okay, this is actually going to be good. So we just added a birth date. We've left it as a double. And this is what we're going to do. We're going to add in, for the first time, a function. It's going to be called getAge, okay? And it's going to return their current age, okay, in years. So we've just, how did I do that? I went to the general properties, I dragged in a function, it's called getAge. Now, when you click on that function, this function is going to do work for us. Basically, a function wraps up to some functionality that does something. And most commonly, it returns a value. Sometimes it changes other things as well. In this case, we want it to return a value. So click on it, and then we're going to click on the left-hand side, returns value. Okay? You see that? Returns value, and it's going to return a double. Okay, who needs TA help? TA help? Okay. Okay, so there's get age. Get age is going to return the age. Now, what we're going to do for the function body, we're approaching 3 minutes here, I think. For the function body, we're going to return the current time minus the birth date. The current time minus the birth date. And I would say that if we measure time in years, that's going to be their age. If they were born at year 0 and it's now year 10, in other words, if the current time is 10, they're now 10 years old if they were born in year 0. If they were born in year 8 and it's now year 9.5, they're 1.5 years old. Does that make sense? Okay. So, ladies and gentlemen, the final thing we want to do, just to make sure that we're all consistent, is we want to go up to the model itself and change its time units to years, just to make sure we're dealing with years. Okay? Okay, so I went to this model as a whole, chose model time units to be years. Okay? Are people okay here? Okay. Yeah. No, basically every time we need it, we're going to call that function. It's actually not being used at all right now, but eventually we'll call it and say, hey, what's my age? And yeah, well, I'll do it in a little bit, but not quite yet. Okay, folks, so here we have people. So now we're going to go into uncharted territory, folks. We're going to now add additional types of agents. We want to add an agent for a workplace, an agent type for a workplace. Right-click on this, you do new agent type, and you say workplace, okay? And we're going to give this workplace a picture as well. So we can go down to pictures in the palette, and we'll give it a factory as the picture. I know not all of you work in factories, but it'll be distinctive enough, okay? So the workplace is going to be denoted with a factory, okay? People okay with that? This is a new agent. It's a new agent type. We right-click on this, we did new agent type, we call it workplace, and I went to the palette, and I went to the pictures, and I dragged the factory over there. We okay? You know? I'm now going to add a school. Okay, so I'm going to add a new agent type called a school. Okay, so now we have a school, and we're going to give something that looks a little bit like a school. I didn't see a really great school picture, but what do you think? The retail store or the warehouse? Okay. So we went to school, and we used by acclamation, it sounds like we used the warehouse. Okay, great. And there's a final agent type I want to give, which will be a home. Okay? It's going to be a home, someone's home. So we're going to have people. They're going to be at home for part of the time. They're going to be at school for part of the time, or at work for part of the time. Okay? And they're going to be exposed to those environments. Sorry? Yes. For home, thank you, Kurt. For home, we're going to draw in a visualization. I proposed a house. Okay. Okay, so We now have several different types of agents. What would happen if we ran the model now? Nothing. Why not? We haven't created any population, so let's attend to that. Double click on main, and let's call in here in this order. Let's drag in the homes. Okay. So we'll call them homes. You drag in, and we'll make them a population of agents, and we're going to make there be, say, 50 homes. Okay? 50 homes. We're going to create a set of schools. How do we create a population of schools? Can anyone tell me? Drag it in there, and we're going to create a population of schools. These are schools that are going to be operating, and we're going to have 5 schools. We're going to have a set of workplaces. How do we create a population of workplaces? Drag it in there, and we're going to have population of agents, and we're going to have 25 workplaces. Okay. Finally, we're going to create a population of persons. How do we do that? Drag it in the same basic shtick. So we create population. We're going to call that population. Okay. And we're going to create 200 people in that population. Okay. Okay. Now, you'll notice that we have to specify something for this population. What do we have to specify for this population? The birth date for each person in the population. We're going to need to give a kind of a formula for how do we determine the birth date. We're going to draw that randomly. Now, the model is going to start at time 0, so I'm going to, perhaps somewhat counterintuitively for you folks, there's actually many ways we could do this, but I'm going to draw a uniform value to represent the people that are between 0 and 65 years old. So this is going to be a birth date between minus 65 and 0. It's just relative to the current point, 65 years ago and now. Are people okay with that? I know that's a little bit weird. We could go and we could set the model to start in 2014, but it's just a little bit easier to do it this way, okay? If anyone's interested, I could show you later how to do it. It probably wouldn't be bad at all, but I'm just doing it between minus 65 and now. These are just relative to the current date. Yes? Yes. You can do that. So any logic can maintain, and I think does by default maintain, fairly confident about that. It maintains actually a calendar of what day it is, like it takes into account leap years and so on. And so you can do that. It's a little bit more mechanism to do it. And for a toy model and for this group, I didn't want to have to sort of worry about the vagaries of creating those dates and so on. It's pretty easy to work with those dates, and you could do it. And you'll find, in fact, I think it's in the experiments here. If you went and you looked at the experiments, you could see sort of what the start date is here and what time of day it is and everything. And similarly, the start time and the stop time. And so in other words, you could use this calendar, and it would enable the calendar time. I think it adds just a little bit of mechanism for teaching. I'd prefer not to do it, but it's very readily accessible, and it's very useful sometimes, particularly if you're saying, is the holidays or the weekend or whatever. If you want to capture dynamics kind of workplaces, that can be quite useful. We're abstracting a little bit away from that, but it's readily supported and it's handy. Yeah. Okay, so folks, the final thing we want to do is we want to make sure these things are laid out randomly. How do we do that? Where do we go to make sure all these things are laid out randomly? Go to main, and go down, and you can go down to this place, to this environment for other agents, and you can go and you can set layout type to be random. Okay, so can we run this thing? Let's run this. And you should see something like this. Who needs TA help? Okay, TA, spring to the fore. Okay, other TA help? TAs? Okay. Okay, so folks, we have a static model right now. What do you think? Maybe we should increase the number of people a bit. They're a little bit. Okay, let's go increase the number of people a little bit. Let's make it 500 people rather than 200, just to make it a little bit more balanced, you know, representative. So you have something like this instead. Okay. Okay. So, ladies and gentlemen, we're going to now. We're going to basically make each person go between their home and a certain location during the day, and then they're going to come back home. They're going to cycle between environments where they're exposed to different influences in those two environments. Okay? So, folks, what I'm going to do is, let's go into person. We have these two attributes, these two features of them right now. We're going to add a home for them. They're going to have a home, okay? The home will be given from a palette. It's a parameter. It's going to be their home, okay? This is going to be the home where they live. And every person is going to have a home. Not every person is going to have a workplace. Not every person is going to have a school. You'll have either one or the other of those. But for the home, you're going to have a home. What sort of thing is this? Is it a double? Is it an int, or is it a? It's a home. It's a home. Okay. So when we create this person, we're going to be specifying their home. Okay. Now, as far as their workplace or their school, we're going to be specifying that in a bit. Okay. But first, I'd like you to draw a state chart. We're going to have a state chart which is going to involve them going between their home and some institutional environment, either the school or the workplace. So how do we create a state chart? Start with the entry point. Thank you. And we'll call it mobility state chart, something like that, right? And then let's drag a state in there of at home, and then we'll drag a state in, at institution, whatever that institution is. It's a school or it's a workplace. Okay? And then we're going to have a transition from one to the other, and vice versa. Okay? No, we don't have to. It's just I like to do it to make them distinctive. But it's a naming convention. Okay, so folks, I'm going to say that they start at home without lots of generalities. They start at home, and then they go from home to institution after a certain number of hours. Okay, now this is going to be interesting. Okay, Kurt, I need your reminder. If we want them to go from home to institution after a certain number of hours, let's suppose after 16 hours at home they go to their. We have to multiply this divide by it's called hour, by hour. Yeah. Okay. Good. I think it's divide. Yeah. Okay. So this basically allows us to specify this in hours. Remember, the time unit we used was year for the whole model. And so by default, we would have had to specify what's 16 hours in terms of a year. but instead we could just do the 16 divided by hour to convert it from hours to years. Yeah. Yeah. So, how would we look that up? Well, if we went to any logic help, we could look up hour. Okay. Okay. Now but Kurt, this says returns a time value equal to 1 hour. So, according to that, I think maybe you have to do multiply then. Right?
I think we can find that by, because the current model is 14 year, right? So if
Yes.
we can just say out in the
Correct.
hours.
Correct. I know. I was thinking about putting a button. Okay. Sure. Let's resolve this. Okay. Great. So let's go to the. You folks don't have to do this, but I'm just going to do this to be sure. I'm going to create a button in main. Yes, Kurt. I agree with you. So let me just do trace ln hour returns, and I'll just do. This is how I'll just press this button and see what it returns, right? If it's something really, really, really small, then that's a sign that we multiply by it. It's the fraction of the year represented by an hour. Okay, I'm pretty sure that's what it is based on that. Okay, there's our button. Boom. Okay, there it appeared. It's really, really, really small. So times 10 to the minus 4. So yes, it is that. Sorry for the confusion. I just wanted to. Yeah. Great. Okay. So with this, yeah, equal to 1 hour according to the current time unit. Yeah. So it's 16 times hour. So this is 16 hours. They go there, and then after 8 hours, they come home. Okay. People okay with that? Okay. Now we're going to make a further change there, but first we're going to do some more work, and we're going to see why that other change is needed. So, no, at their home. They're going to after being at home for 16 hours, they're going to go to the institution. Yeah, this is a timeout. After they've been here 16 hours, they go home. They go to the institution. And then vice versa, they go after 8 hours. And we're going to call this, return home. Maybe it's return commute, commute home, commute to there. And this is go to institution or something like that. Okay? Great. Okay. That's good. But we need to pick to what institution they go, right? Where are they going to be going? To what institution are they going to travel? It'll be either or based on their age. If they're less than 18, they're going to go to school. If they're more than 18, they're going to go to their workplace. Okay, so we're going to put in a variable that represents a variable note here that represents their institution. Okay, what type of variable is this going to be? It's going to be a. Okay, it can be an agent. It turns out it's some agent. It's either a home or it's either a school or it's a workplace. Either one is an agent because it's not told to them. They're going to determine it here. If a parameter will be told to them, and they're going to determine this based on their own age and stuff like that. Okay. Okay, and when they get created, we're going to when they get created here, we're going to determine their institution. Okay. In fact, right. we could do it right here. Yeah, here we go. Okay, for this variable, for the initial value of the variable, we're going to call the get age. So if their age, if yes, that's a nice idea, Kurt. Sure, sure. Okay, I like that idea. Um, sure, sure. Okay, so we could do it in fact right here. So when they leave home, if their age is less than 18, or less than or equal to 18, then they're going to go to the nearest school. Otherwise, they're going to go to, we want them to go to the same workplace every time though. So we need to determine it once. Um, age actually is changing right now. This get age, because as time advances, remember get age is defined, it's the current time minus the birth date, so it's actually, they're going to be aging over time. So Kurt's right. So we could have them go to the closest school. How about for their workplace though? Sure. Okay, sure. Rather than institution, we'll make this workplace in school. Okay, I like that. So we're gonna make this their school, school. Yeah, closest school. Good. Closest school. Yeah, I like that. And the closest school, folks, is going to be of type school. And what's its value going to be? Well, we have to ask what's the closest school to them. So we're going to call this dot get nearest agent, and give it a list of schools. Where can we find the list of schools? Sorry? Where can we find the list of schools? Yep, and where does that live? That lives in Maine, so we have to say Maine dot schools. Okay? The closest school is going to be obtained from there. And then we're going to have a workplace. This is like the workplace, workplace. And the workplace will be what sort of type? Folks, what sort of type will that be? A workplace? So I should have waited with closest school. In case people want to see this, this is what it is. This is what that is. Get nearest agent, Maine dot school. That's closest school. This guy here, he's a school. And this is how you get it. Does that make sense? We're asking Maine, hey, give me all your schools. And then we're saying, get me the nearest agent among those schools. And it gives me the nearest one to myself. That's why there's this. Me, from me. Say, hey, myself, what's the nearest school to you? We don't have to, but it makes it explicit. I'm asking myself, what's the nearest school to me? So, question. Yeah. I called it schools. Up in Maine. It's called schools. Schools. Yeah. Okay. And then yeah, occasionally they use self in here instead of this. The semantics is so. I wish I could give you the best answer, but they use functionally, yes, you could think of them as being the same. In general, 99% of the time, you're going to use this. Self is in any logic thing they use in certain contexts. And the more fundamental thing is this. You only use self when it gives you that little blibbit. It says use self for such or such, and you use it then. Okay. Oh, it just says press Control Space if you want to, Control Enter if you want to refactor it, if you want to change it. This is kind of useful. If you go and you change the name later, you have lots of things to refer to it. You can press Control Enter. It'll find all the places to refer to it and change them all at the same time. Okay, so we're going to have a chosen workplace. Ladies and gentlemen, what sort of type is this going to be? It's a workplace. Yeah, it's a workplace. And we're going to choose a random workplace. Okay? A random workplace. So we're going to do main dot workplaces. Ooh, main dot. Oh, it should have been called workplaces. I think it should become workplaces. Sorry, I called it workplace, but it should have been workplaces. Okay. So chosen workplace. The initial value being main dot workplaces dot random. In other words, pick one randomly. Okay? Okay. Now, there's a good question someone may ask about why not make the chosen workplace a parameter, and we could have done that, and another way to do it. Okay. So here we have chosen workplace is a workplace, and its initial value is main.workplaces.random. It chooses a random number, random one from the workplaces with uniform probability. Okay? And now, when they leave home, what would the logic be? If they're a child, then go where? Good. Otherwise, go to the chosen workplace. So if this get age is less than or equal to 18, what would I put here? Remember this? Question mark. Good. They go to the closest school. Otherwise, they go to the chosen workplace. Okay? Which is not necessarily the closest one. Sorry? That's the syntax. Oh, thank you. Yeah, sorry. Thank you. Actually, I do need to do, okay, so what I'll say is, what's the nicest way to do that? Oh, okay, yeah, this is what we'll do. Thank you. Get position, or get location, I think it's called. I'll close the school dot get, I thought it was called get position or get location. Get position, that's what it is. Get position, and otherwise we go to the chosen workplace get position, okay? And, oh gosh, we could do this better. At the cost of, I can't stand not being elegant about it. This is what we want, and then we want this dot move to this whole thing. Yes. There we. Okay. Oh man. Yes. What, say that again, Kern? Okay. Oh god, it's packing too much into one thing. This is gonna be confusing to people. Sorry, I'm gonna unpack this. I'm gonna just say agent destination equals. So the destination is either the school or the workplace. Boom. And then we'll move to whatever the destination is, position. Okay. I'll put it up. There we go.
So what does that mean?
This is basically declaring a convenience variable that says, I'm going to give a name to the destination, okay? And this is the logic for it. If I'm less than 18, it'll be my closest school. Otherwise, it will be my workplace. It'd be the chosen workplace. Once I've given that a name, I could say move to it, position. Okay. Maybe I should have put this in parentheses just to be extra clear. This is confusing to people. So basically, okay, if I'm less than 18, my destination is my school. Otherwise, it's my chosen workplace. That's the results of this whole expression, this whole formula is going to give me my destination. If I'm less than 18, it'll be my school. If it's more than 18, it'll be my workplace. That's my destination. Wherever my destination is, get the position of it and move to it. Move myself to it. Does that make sense? Okay, who needs TA help? The TA sit ready. Okay, TA? Sorry? Yeah. Yeah. So here we're declaring, we're declaring a name for this destination. An agent. Are both agents. Yeah. Either one of them is an agent. We're actually not creating, we're just giving it a name. We're, yeah, it's a variable that holds the name, sort of the reference to it. Okay, this is saying, okay, on myself, to move myself to this place, to this place. So this is this is like the subject of the verb, and this is like the object of the verb. This is like who is doing the moving, and this is to where they're being moved. Say that again. It's asking for the destination, the position of this destination. No, because it's something that we're asking of the destination. What is your position? Yeah. Yeah. It's possible. It's a procedural way to do it. It's a different way to do it. So for the interest of time, I haven't had coverage of Java in this. If we weren't doing project work, I could do much more thorough coverage of Java. But in this case, the basic idea is that for the most part, things in Java are responsible. If you want information about them, or you want them to do something, you address them directly. So if I want myself to move, I call move to on myself. If I want to get my position, I would call this get position. If I want the position of this destination, we call the destination get position. Because I address my request for information and someone to do something to the person that is responsible for that. Yeah. You could think of it as virtual equivalent to the first argument, but you could think of it as a function that is the virtual equivalent. So it's basically asking this guy to give it position. Yep. Right. For the language, I have a bunch of slides which I've provided to you on the example slides on the Dropbox, which go systematically and cover this. And if people saw this as a really high priority, if you want me to take 2 hours, I could do pretty good coverage of this. It's just what's the opportunity cost? Yeah. great feedback. I actually had it in the schedule originally, so we can make it happen. And I think it would be quite valuable. I agree. So yeah, why don't we make that happen? Okay. Yep, we'll do it. I'm gonna have to look at the schedule. It'll either be today or tomorrow. I'll do that. Okay. Great. So I appreciate that feedback. It's actually very helpful for me. Okay, so let's build the model. And now let's so TAs, you may be needed right now, particularly if people encounter problems with that. Let's run the model now. This is the model simple continuous mobility. So let's run it. We should see people moving around. Do you see something like that? Okay. Okay, let's. Okay, yes, they're moving very slowly. That's why they're moving at glacial speeds. Okay, okay, folks. So we didn't set their speed. You think the commute in LA is bad? It was taking them years to reach their destination. Okay, so folks, we're going to set it so they move faster. Okay, I'd like you to go to the mobility state chart. Okay, so there's a question here? Okay, do you have them set to move here? Okay, move significant. Okay. Sorry? Oh, thank you. Yeah, that could be. That's a very good point. Let's go deal with that issue. So let's go to Maine. I can't remember if we did that in this model or not. Let's go up to Maine, go to the population here. We didn't set their home. That's one. Yeah. Okay, so go to the population, and their home, folks, should be set from homes.random. So this sets their home. Okay? So we went to Maine, and we set the population to have a home that's chosen randomly from the set of all homes. Okay? Okay. Now, I don't know if that will solve the problem for she, but that will certainly help here. Okay. Well, that's because they arc themselves in a certain angle. We can change that. Okay. So what I did, that last thing I did, I went to Maine, and I set for the population, the home for each person be given by homes.random. So in other words, you pick a random home for the person. Okay? When they first go, this is a very good question. When they first enter, we should really have them go home. So when they enter this at home, okay. Sorry, folks. Too tired today here. Okay, so when they go to this at home state, let's have them actually go to their home. So how would we do that? How would we have them go home based on that earlier thing we wrote? What would we do? This dot move to home dot get position. You have to move to the position of the home. So when they go into this at home state, they're going to move to their home. I'll put this on this, sorry, there it is. That's what we, so here we're determining the position of the home, and we're moving the agent to that position. For anything where you're telling it to do something, yes. If you're telling it to compute a value, no. If it's a formula, no. If you're telling it accomplish this, yes. Kurt? Okay. So we still have their speed. Oh, look at that. they're exhibiting twerking. Okay. Okay. There's a defined reason for this. Okay. So the reason is they are taking years to go, and so within each commute they exhibit reversals as to where they're going. So folks, let's also set when they first come into the state chart, let's set their velocity. We're going to set the velocity when they come into the state chart. This dot set velocity to be such that they can easily reach in the course of a day, they can easily reach across the space. In the course of an hour, they can, say, cross 100 time units. So, or 100 spatial units. So I'm going to divide 100 by 1 times hour. So in other words, within 1 hour, they can go across 100 units of space. Okay. So now they have for some of them it's still going to be a long commute, but I think you folks are familiar with that phenomenon. So what did I do here? Let's try that again. And this will stop the twerk. I wish I could say so about the external world. Okay. So this is what happens. Within a span of 1 hour, they can cross 100 spatial units. That's the velocity they need. 100 things per hour. 100 spatial units per hour. That's what this says. Okay. So now let's see how fast they are. Let's give it a try. Okay, let's slow it down. Okay, so what's happening here? Can anyone describe what's going on? Well, you can stop the whole model, but it's going on. They're going back and forth from work to home, or to school or work. Some people are going to the schools here. Right. Yeah. Yeah, it does. Because we're actually asking for that. No, that's only 4 years in. I slowed it down to see these patterns. If you want to speed it up, after a certain point, yeah, see, like no one's going to the school now. Okay, and now we have increasingly a population of Methuselahs. These are talk about an aging population. Okay, so here we have a situation where we captured this kind of cycle between work and home. Some people go to, well, here, let's start it again. Some people go to their workplace, some people go to okay, hey, no, sorry. We need to restart the model entirely. Let's not just, okay, there we go. Right, okay, yeah, okay, oh, that's not, oh. Yeah, I agree that what's going on with those schools? The age of the population is uniformly distributed between 0 and 65. Yeah, yeah. Yeah, because let's go take a look. In Maine, in the population, it's uniformly distributed minus 65 and 0. And we certainly saw that earlier that they were going to schools. Okay, let's try this. Let's see if they are going to the schools. Every time they go to a school, why don't we? This would be that's easier said than done. We could keep track of how many people are at that location. That would be one thing we could do. Okay, so let's experiment with this. Let's suppose we were to set this population to be all younger people. Let's take the birth date to be from so everyone's 5 years or less in age. What would we see then in terms of movement? Okay. Looks like they're going to the same school. Wow, that's pretty neat. Okay, they are indeed going to a school, but it's the same one. So what's going on here? Let's take a look at this. Okay, the closest school is the nearest agent in schools. Okay. So why is that the same across all of them? The nearest school is in common between them. Okay. Their workplaces are the same. Okay, now they're going to that school, so it's replicable that they seem to consistently pick just a single school that's closest to them. Oh, I know why. Okay. Got it. Yes, that makes sense. So what's going on is that they don't actually move to their home until they get into this state. And by that point, they've actually chosen their school. They actually don't originate, where their home is. Now, why they're all being mapped to that school, I'm wondering if they're all originating in the origin. But we could pick the school once they've reached this state, for example. Okay. Nice hypothesis ruined by an ugly fact. Here they seem to be going to that school. Okay. So let's do this. Let's set their closest school to be given by when they get their position. So where are they starting? Could be starting randomly distributed. That's a funny thing. Yeah. And all the factories are visited, right? Okay. Well, Well, yeah, they later they're visited, okay, I think. Yeah, it's somehow they're all getting the same range. Let's just go read this in case there's something. Returns the nearest agent from the current population. Um, yeah, okay. Okay, well, I'm gonna have to investigate that. What we can do right now is just have them pick a random school then, I guess. This dot, so main dot schools dot random. Let's see if that works. They should at least be going to separate schools, no? Right? Yep, they're going to different schools. Okay. Yep. So what I did is I set instead of saying the closest school um, is get nearest agent, I did main dot schools dot random. I picked a random school. Correct. Correct. It's not dependent on their current position. That's right. Yeah, at least that's a very common use. Yeah, yeah. So obviously, if there were a problem, I'm going to have to look about why that is. That it wasn't picking that. We could obviously manually determine the nearest school without problem, but yeah. Yeah, I'll look at that. It may be some trivial thing. In any case, big picture here though is that these agents go back and forth between home and an institution, and at each place they're subjected to different influences. They can be subjected to different influences. So at home, they'd be subject to influences from the environment of the home with different nutrition, different physical activity norms, different patterns. At the institution, they would be affected by the situation there, whether it's the amount of sodium in the cafeteria of DPU, or whether it's some aspect of the school lunches or the physical activity programs at the school. So this model basically captures that back and forth between those two situations in the course of a day, and moreover, it illustrates this kind of mobility. Because we set the time unit to be a year, it's going at a minimum very quickly, and so we can't really slow it down beyond 1/500, which is really too bad because we could see the kind of movement of people across the space. But right now, they are spending different parts of their day in different places. Let me switch it back so we have a mixed population of people who are kids and people at work. So here the population will be between -65 and 0, and there we go. Yeah, okay. So now we have kids going to school, we have people going to work, and right, okay. There must be a house just below this thing. That's all I could figure this why that person's still there. Okay, so obviously if you were to have a model like this, now you could capture, because we have this within a person, we could total up their influences while at home and total up their influences at the institution. We know which institution they're at, the workplace or the school, so we could ask, what's their exposure levels at that place, and total it up on some aspect of their health state. So if we wanted we could build a separate state chart associated with blood pressure, or associated with salt exposure, or associated with level of physical activity, and during the time they were at home, it will be affected by that. During the time they're at the institution, it will be affected by that. Okay. So, yes. Sure. Oh, the return dome, there's nothing here. There's just, when you come into the state from either this or that, you do this dot move to dot home does it. Yeah. Okay, good. Any questions about this before we break? So this shows an aspect of mobility. Just to give you a glimpse of another model like this, there's actually two models I have that are like this. One of them I've provided to you, and I'm going and looking for it here. I think it's this one that I've provided. In this case, we have homes, schools, workplaces, and we also have shopping. And so people go between the homes, and then they'll go to school, and this, it sizes these things according to how many people are in them, and then they'll go shopping and go out and stay home. So if you go look in this model is in your example models. It's an infection transmission model, and they're at home, they're at an institution, they're engaged in outside activities, and then they go home. And this bar underneath here represents the level of infection in that particular place. So you can go check that out if you were interested. Yes. Right. They're on a very similar cycle. So here it's just some fixed timeout, like it was the model we just saw. By contrast, over here in this state chart, you have things that are rate transitions, I think, and so on. But for these, they're on a fixed daily cycle. So after they're a fixed cycle. For that, it so happened. I mean, we did that in a fixed way. If we went to person here and we changed it so that instead of being a fixed timeout, it was based on a rate transition, it would be stochastic. Or we could have, for different people, they spend different times at work. And so, some people might spend a longer time at work and some people a shorter time, and we could choose that randomly for each person. Yeah, right now, but again, I mean, you could pick how long they spend at work randomly on a per person basis or a per occurrence basis. In other words, on a per day basis. That would be a very straightforward thing to do, and then people wouldn't be synchronized in that same sort of way. They would no longer be in sync. And in case you want to see what this is like for when you have this model on a slower time constant, this is what you get. This is another model where I didn't have continuous aging, that I just built as a sort of test model. And here you could see people moving more slowly. The rotation of people you can set if you want to. So you can set the rotation to be fixed, in which case they won't actually rotate while they move. They'll just move across the screen in an unrotated fashion. Okay. So any questions about that? Any questions? No? Okay, so, we'll, get back together here in, what, maybe, we do, an hour today? Or are people good with 45 minutes? An hour? Okay, we'll do an hour. Okay. Winchell or Kurt, could you try to sleuth down why this closest school thing is not yielding? Okay, so here, come on up here, I'll show you. Yeah, yeah. Okay, so we'll be back here in an hour, right, at 1:40. Yeah. So this was set to be, the closest school was set to be this dot get nearest agent and main dot schools, right? And it was always choosing the same school
Oh,
across agents.
yes, yes.
And the question is, why? I wouldn't have expected that behavior. So they're all linked to the same school. There's only one school that's being occupied. This school here. So it's a house behind it. So yeah.
I'm not quite sure what that is, but I saw that this is being set in with the in the agent, right? They didn't say that? Will there be any difference if we put
As a parameter?
yes,
Well, the problem is that I want to call for the agent, what's my nearest school? And that's hard to do when you pass it as a parameter.
just for clarification,
Yeah.
we just can trace element for
Sure.
to see which is the nearest school. This is trace element the same.
Well, we can't do it right here because
Yeah,
it's
yeah,
expression,
yeah.
but we could,
Is there any action to move to school? If there is, we can bring it up.
report closest school.
Yeah, because this only set once, right?
Right, so we could do it at time 0.
Yeah, and we don't need
And
we don't need to alter it. We don't need to reflect it. And we can trace out later.
yeah,
I can also put some clarification.
sure.
So we just put person, then the just clarify how the as the application on the application because we are always
Wait, you dragged, oh,
over
oh,
yeah,
there.
it's really hard to distinguish.
I see.
And let's
See,
do something to
here.
do that. Yeah.
Oh, look at that,
They're different.
they're different.
Yeah. So maybe just because something happens wrong in the animation, could we reduce the number of populations we can fit clearly, and also the number
Okay,
of
yeah, so that's really interesting. Okay, so let's see here. Okay, so let's try,
Steve, you're destination, you would say?
um, yeah, yeah, see, it's all set to that now.
Oh, interesting.
Isn't that interesting?
Yeah.
So it's somehow been reset or something.
Yeah. Did you set this interesting something basic?
No,
Actually,
no,
it shouldn't be.
no, it shouldn't be, no.
Okay.
So the question is, why isn't that set by the time that they're here, right? Or why has it been reset? Okay, let's just make it single agent, single person, right?
Yeah.
make it a single person in the population, and then we can see them, and let's make it, we should really copy this.
We can save it as.
Yeah, let's do save as this model, save as save it as a model. Okay, uh, debug,
Or probably different.
yeah, right. Okay, so initial number of agents, 1. Let's make them all kids, right? So let's make them all, no, 0. And then let's run that, and then we'll see for that particular agent what's going on, right? Okay,
Oh,
great,
yeah,
come on.
okay, so it's that.
So it appears, but let's go see if we can see their initial. See, okay, it
Initial
sets
is
their initial
1.
score to be 1 here, but then later it's set somehow to
Wow.
be 0, right?
Yeah.
Okay. Okay. So something curious is going on, because here it's set to a correct thing, and here it's
Can you search what processes do?
see if it's used somewhere else.
Yeah.
Yeah. Go to institution. Yeah. Yeah, it's just there. Isn't that interesting?
That is interesting. Oh.
Yes.
Can we get one for you guys? Can we go and bring it over?
Oh, that's too kind for you.
We can go to Louval, or we can go, May's not here, so we can't go to Hawkins Center, but we can go to Woodland to Cafe, we can bring back a sandwich, or
Oh, wow, that's
what
great.
would you like? There's everything. There's pizza and salad, there's rice and pasta.
There's something veggie for me,
Veggie?
if we could, yeah.
Okay.
And anything from me also.
Okay, you eat anything? Okay. More on the heavier side or lighter side?
Heavy.
Heavier side for Oscar?
Well, like a sandwich type of thing, like a veggie sandwich is great.
Okay.
Yeah.
I heard that to be healthy. Sorry.
No, so it's lighter or heavy?
Yeah, let's look at that.
Diet?
Yeah. In terms of also vegetables.
Vegetables?
Yeah.
Okay, all right. Can we get you something to drink?
No, that's okay. I'll just take the water. Thank you so much. I'm sorry to make you. I hope that won't inconvenience you too much.
No, of course not. This is helpful.
Okay, that's fantastic. Yeah.
Yeah, definitely.
Great.
And then, Phil wanted me to let you know that he can't make it today
Okay.
because of the flooding and
Oh, well.
the water. But we're gonna try to have him start in and then do the group discussion.
Great.
Do you know about when that would be?
Um,
Or I can ask you later once.
why don't you
guys
ask
have-
after
yeah.
lunch?
Okay.
Yeah. Thanks.
Thank you.
Okay, this is the most peculiar thing.
Yeah, if we find a bug, that will be interesting. And then we can let Annie let them know that. I mean, sorry.
Okay, so let's go up here. Let's print it out here.
Okay, Nate, I have a question.
Yeah.
I thought, I may be wrong, but I thought like we could set the closest to the non-variable could be a parameter, right?
No.
No?
No, because, well, I mean, in general, we want to determine by calling get nearest agent, and that has to mean the person's attributes have to be set by them. And I think by the time the parameters is computed, I don't know that their X and Y location is set.
Yeah, that will be some like first or later on in the initialization.
Right.
Is there any dependence that? But yeah.
Let's
Oh, my thought would be just if we can find any way to prevent it to be resetted, then we can know if there's any reset happens which causes the problem.
well, we could with aspects, right?
Well, that's for sure. But if we set it to be a thing that cannot be changed.
Okay, let's go mark these to where they're occurring, right? Man, I'm dead tight. possibly,
that
but,
will be
but let's,
your-
stop this, okay. So all of these are that, okay, let's, oh,
You didn't set a school to die out, right?
sorry?
You didn't set a school to die out, right? There isn't any like a death
Here we go,
rate for
look at this,
right?
look at this.
Notice just do it. And then it says you want.
Yeah, but look at this. It's almost like something, well,
Can you
okay,
filter with the
okay, number
font?
3 is probably this one, right? And then this one, okay, so they enter the state before it gets set, and then this thing is set, right? But wait a minute, report close to school isn't fired off until time 0, and then that, yeah, report, and then, and so by this time it's set,
Yes.
and then it's like reset. But I don't know that I believe the order in which these are occurring. Remember Priestley said that they're not always in the correct order? I don't understand what could be going on. That's really interesting. Again, aspect.
Yes, but now since you can create this model to be another version with promotion with aspect on it. For now, if you don't use aspect, obviously one of them is possible, right? If permit, I mean, just let the code the school to be setting one to see if you later, and we print if later time somebody wanted to reset it. If we print it every time it's gonna to reset, it would be possible to do that.
Print then every time that it's reset
Yes.
using what? Can we do it debugging here?
Yeah, I think we can do that.
Okay, so how do we set that to can we tell it to like set a watch point on it or
I don't believe they all will for anything. Unfortunately.
well we have to go into this, right? Can we
If we want to run that, I believe someone.
yeah, no, I'm looking for watch point, setting a watch point so that it will stop when you reach a certain.
I believe here variables, and if we right click the tab, probably it should be showing something which one we want to add. No, just right click the tab here.
Expression,
It will be updating right now.
that's the thing, yeah. I don't know, it's tempted this to be something, but I'm gonna stop this, but yeah, I'm utterly flummoxed by that. Tell you what, let's stop this from occurring altogether. Yeah. Yeah, I spoke with Hava already, but yeah. So let's make this you know the question is, could we, let's make this condition false, so that we never go there. Let's see if it still occurs. What do you think? Right? Okay? Okay, so now let's set this to be, to go periodically.
Yes, I'm just trying to.
Okay, sorry, I'm not thinking clearly. Terrible.
I know.
Terrible. Okay.
Okay, do you want some cool weather?
Okay, look at that.
It changed right?
So it never changes back. Never reset. Once it's set, it's correct.
No. I'm missing something wrong with the
Look at that.
Thank you.
So now it's working, okay?
So it must
Something here,
here.
or here, or here.
Yeah, it must be here. Then
Okay, let's comment these things. Let's just comment those out, right? Right?
oh,
Well, and then let's re-enable this thing. Make it a timeout of that, right?
yeah. Then perhaps something wrong with the definition for section 89 or something.
Yeah, okay. Let's slow this thing down, Keisha. Oh, okay. See that? Now something here. Yeah? Yeah. Wait, say that again? They're low, location. Yeah.
If the current location doesn't change, then there must be something wrong with the function of getting closer to P. If the location change, then we know perhaps there's something wrong with the other one. We just want to
Sure.
go further down. I mean, just within this function, if it happens something where within this transition.
Well, wait though, because they may be moving from this transition still.
Okay, yeah, that would mean then.
Um,
Oh, okay. So this person got like the phone. Is there all these things? Couldn't be. But the closest to P is the function of
well, no, it's just this variable.
yeah, but somehow they have this.
Well, it shouldn't. That's the thing.
Yeah.
There should be nothing that modifies this, right? Here, let's try this. Let's make it a. Well, no, it can't be. Because it's not defined, and it's clearly
Oh, the function is meaning like
final.
you can set it later, but you can only set it once. It doesn't mean you have
No,
to set
you
it
can
once.
only set it in the constructor or the declaration.
What is in the function as long as you didn't set it twice?
I don't think so. I mean, we can give it a try, but I thought that you can check the Java definition, but let's try this. Sure, let's give it a try. No, cannot reference to the first. Oh. huh. So I'm still really puzzled, right? Timeout, so again, Paul, okay, oh, that's interesting, it gets reset. Look at that, you see that? It got reset.
Even if it's
Well, then again, it could have been a fluke that it got the same. Okay, you know, it could have just picked that one, but it's not getting reset here. Okay, the question is then, is it something that occurs here? Is it something that occurs here? Or something that occurs here?
this part of the result isn't important. So the coding always choose the closest to what is that H1. So here, simply you use this one, but every time you just wait. The last time you
Well,
go to the closest.
but you see, I mean, we don't, that's the really interesting thing. We don't need this line or that line to reproduce the error. Oh wait, sorry. Yes, we don't need it. I mean, in the sense that if you had this as a timeout here, it still has the error. It still exhibits the error.
So that leads me to the question whether
Let's just,
where is it? You like how did you set the home initialize the home for the person?
say that again?
How did you initialize the home for the person? Did we choose a random one for them?
Yeah, it's a random one selected when they're initialized.
Okay, thank you.
Sure. Right there.
But I was wondering, I know it's scary now, but could we put those things in every person?
Sure.
So we can ask every person.
Delete the parameter.
Well, we can put it there. As long as you set the person's home to be random. You set a default value for that.
No, the default value is just the value. That won't change how it's computed then. We need to change it to a variable, I think.
The variable will be changing all the time.
No, but this default value is not its initial value.
Oh,
Default value just means if you don't specify it with the parameter in the population, that's
Yeah.
what it's that's the expression that's used.
yes, and then every person will get recompute as a home randomly. But we need a
No, it's the same thing as before. Basically, this is the same semantics as this.
Yeah, but the thing I was wondering is whether this only called once. It only executing once in the main, and then just copy all the random things to every person. But another way to check it.
But that is not going to impact their school, right?
But if the persons are all go to the same place,
Yeah.
are all initialized to the same place at their location, then it'll be impact on what is their place at the school, right? If they're all standing at the same time or at a certain moment, then they all choose the same school. I don't know.
Well, yeah, but they're definitely not. I mean, but this is the same exact semantics as before. I mean, it's the exact same thing going on as before.
Yeah, it should be.
But we can get rid of, well, don't quite understand why this, why it is.
The person, does the person moving?
Yeah, the person's moving, but we can get rid of this moving,
Yeah.
and we don't have to. Let's try that. I like that idea.
Can you get, no, we need to delete the whole. Initial value for what default value for the whole. Otherwise it becomes wrong. But in the home?
Why is that? Why do we have to delete it? No.
In the home.
Why?
This one?
Yeah.
That'll be wrong because we cannot find home in person. If you want it to be correct, it should be man.home.person. Initially.
No, this is actually evaluated in main.
Okay.
That's the thing. This is not actually evaluated.
Okay.
It's not an initial value. It's a default that would be. Thank you so much. Wonderful. Grateful. Thank you so much. See, that expression is just the expression used here. It's actually evaluated in this. So it's actually not evaluated in the person. It's evaluated. At least that's my distinct recollection of it. But in any case, we're not going to use its value now. So let's try this. Okay. Okay. So that's. Okay, let's take it. Yeah, see, it's still reset, even though there's nothing going on here. Let's print out the time, right? Oh boy.
We have to delete the second.
Okay, let's try that. No. Oh. Okay. What do you do?
Okay,
I think I have a hypothesis
Yeah.
about what's going on.
about the initialized system.
Yeah, precisely. Okay, yeah, so basically the variable is not initialized to the value, but it actually does report the right thing. So basically, this guy is getting initialized before the person's location is getting initialized.
Yeah, and then it'll
That's
give
the
them
issue.
every person's location.
It's zero.
Can we double check that? We can, because we know the
Yeah.
person's initial location. So we can just get a trace person for the trace person, or whatever. We just get the
Well,
address to
well,
closest.
no, here, we could do trace ln. My location is,
At this moment.
yeah, this dot, get position,
Yeah.
right?
Yeah.
Right?
Yeah.
Oh, boy. Okay, let's just try that here. Boom. Okay. Oop, oop.
0, 0.
Yeah. So it thinks it's 0, 0.
Yeah. So basically, we need to trigger.
So that's no problem with that.
Yeah.
Then it's very, very simple. We just initialize it, I think, when they come in here.
Yeah.
There's zero problems with that. So let's go open the model. Here we are. Okay. And let's go fix it. Right? So instead of being computed here, we put it in, or in the initialized thing for this. Closest school equals this document, right? And now let's try it, right?
I think it works.
Yes. Yes.
We can see the print here.
Yeah. Yeah. It's working. Nice. Thank you, Vincent. Okay. Well, I'm wondering, I think we're not supposed to evening. Yeah. It was so basically the variable is created before the person's position is set. Okay. Yeah. 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 It's a very simple one-line fix. It just went like this. So instead of initializing it here, you initialize it when they enter here. I have two. I've seen it too. Yeah. So which is yours? Which is mine? Say which one is mine. I don't know. They look like maybe they're the same. They seem to have the same bucket. That's what yours is. Eon to Eon. Yeah. Okay. Hava, thank you so much. That was just wonderful. I'm really grateful for you going and doing that. Keep on to you. It allowed us to debug that model. Um, it's just something with some vegetarian options. Something with some vegetarian options. No, that's all. No, that's very kind of you. But, can't. Um, I don't drink, so I don't know. You know, nothing where liquid beer. That's about all. Thanks. Thank you so much. Oh. Mm. We found what the problem was. The agents, at the time that variable was evaluated, that initialized, the time that get close to school was determined, the agents didn't have a location yet. So in other words, the variables determined before their location. So all I did is I just added it to the, I'll show you. All I did is I added it to the state chart instead, and so you just put it here, closest school equals this. Yeah. I think I was printing out what the closest school is for that agent, but that was determined at a later time, not at the same time. So now they're going to each school. Yeah. That I've seen that error before. Kurt has seen that error before, and it's a little bit confusing. Are these things computed before parameters in X and Y? Yeah. 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 I actually think it's pretty well defined, and I remember it at one point, but I don't remember it now, and this is an example. Yeah. So I would have thought that before those got initialized equals X and Y, but I'm misremembering that. In any case, it's easily dealt with. You just move it over to here, and at the point they come in, you set it. Sorry? Yeah. Sure. Yeah, in building the model, that one has to be added first. Yeah. Indeed, totally. Mm-hmm. Yeah. I mean, it's something you might not anticipate at first, right? Right. 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 So you decide very reasonably later, and then you have to go through this ritual of like removing that parameter and adding it back in. Mm. Into continuous time? Yeah. Yeah. I did the same thing last night. Yeah. Yeah. Right. Right. The other thing I played around with was if you were to give them a more rather than a Euclidean neighborhood. So, because right now, well, it's very coarse grained, right, in the sense that you can only have 0, 25%, 50%, 75%, or all of your neighbors. And second of all, I examine the impact of if you have more than two types of groups, how that generalizes. Mm. Mm-hmm. Mm. You mean the sort of proportions of the different groups? Yeah. Right. Yeah. Mm. Yeah, I mean, right, right. So yeah, I mean, basically, you have the number of groups minus one, degrees of freedom, and you gotta specify, you can specify that many fractions. Oh, I see. Hmm. So I must be missing something. So, okay, maybe okay, I interpret one way that could be problematic. Are you talking about leaving? So in my model, basically, it was flexible. You could specify in the experiment how many groups you wanted to have, and the colors with which they're associated, and we'll use those. And in that case, yeah, you'd have to specify a vector of, a number of groups -1 sort of values, and then presumably specify a total number of agents, and then in the I'm trying to think in the exact code for it. Yeah, you'd have to draw from a multinomial distribution, basically. Right? Yeah, Apache stats library is what I use with any logic sometimes. Just attached to the jar file. So I'll show you. So in I actually have a. If you wanted to see actually a model with this, I could show it to you. But okay. Weird. That's weird. Yeah. Try that again. What's that? Indeed. Yeah. Okay. There we go. Yeah. So in any logic, you can go to if you have a thing here, you could say jar files and class files required to build the model needs to be arbitrary Java jar files. So you can go specify, an Apache stats. And Apache stats, I'm pretty sure would support. It's part of the Apache project, and so Apache statistics library. Oh, well, let me try that again. I've been having trouble here. Actually, Kurt has as well, where we get kicked out of certain of the network. Hmm. Oh, here we go. So I'm gonna put this search here. I would just look under Apache statistics, but I can find you the one. Here it is. No, it's Apache Common. It's Apache Common statistics. Yeah, maybe it's Apache Math actually. Oh, I think this is it. Yeah. I don't know. Maybe it doesn't have multinomial. Hmm. Apache Commons Math, but I look for multinomial. I'm not finding it. see that they're saying a wish list sort of thing in here. Hmm. Well, oh yeah, sure, absolutely. But looks like there are other libraries that do that. This might be suitable. Although I don't see where the sampling from it is defined. Maybe it evaluates the density. But anyway, I gotta prepare something here. So that looks to me like looks like this is multinomial sampler as part of this so-called Mahout math library, as part of Apache. So you might consider that. MAHOUT, multinomial, and it does sampling of it. Okay. It was a silly little thing, but, yeah, yes, thank you, thanks to Taba. We were able to get that. Okay, great. Terrific. So folks, I just wanted to recap one thing about that last little exercise with which we were working. Happy to report that that the issue was well fixed now, and it was a silly little issue. It's a good lesson, and I actually thought we could use the chance as an opportunity to make it a little bit clearer. This won't take more than about 10 minutes. Yes, Kurt? Oh, thank you. So some of you may remember in the time before lunch, we were, so I'm going to actually stop this. In the time before lunch, we were working with this model where we had people at home or at institutions. And there was some peculiar behavior being exhibited whereby all the kids were going to the same school. And we were trying to figure out why. And it turns out it was because this closest school, in the closest school here, we were determining what was the closest school. And it turns out the value of this was determined before someone's position was set, before they actually was determined where they were in space. And as a result, everyone was assumed to be at the origin, at the home location, and everyone is assigned to the same school. The answer to this, the solution is very simple. You just assign to the school, the closest school, when they come into the state chart, and you'll be fine. So, having done that, we are in a situation where we have the agents going back and forth between their homes, as indicated here in blue, and in their workplaces, as indicated in red, or their schools, depending on their age. But this is an interesting example of a model which, like most models in any logic, can be approached in many different ways. And one of the ways that a model like this could be improved to make it more transparent, I realized we should have done, and I'll talk about it right now. And it'll be actually an important point of learning about state charts. It'll highlight something at state charts we really haven't tapped into strongly. Maybe once we used it. So right now we have this transition which is a little bit opaque to most people. People weren't sure how to interpret this. Basically we pick a destination, then we move to the destination. And I realized it could have been done quite a bit more nicely by instead of just saying at institution, have two different ones. This would be at school. This would be for agents that are adults. Maybe I'll move this guy over to the left-hand side here, just so it's more clear. And then I'm going to add a separate state, which will be specific to adults. So at school is specific for kids, and a separate state specific for adults. And this would be at work. And we would have very similar logic here for the at work case as the at school case, very similar timings, etc. So I'm just going to copy these things up to there. Boom. So after 16 hours, they go to work. After 8 hours, they come back from work. But having done it like this really simplifies things. All we have to say here is to go to work, they move to their chosen workplace, and down here at school, they move to their chosen or closest school. And the key thing that we need is what? Does anyone recognize it? What's missing here? Sorry? The guard is missing. we need a guard which basically says, under what conditions do we do this or this? Under what conditions do we go to work versus school? And the guard, of course, will be what in this case? It'll be based on their age. So the guard here will be, they will go to work if their age, get age, is greater than 18. And similarly, they would go this way if it was less than or equal to 18. That'll be one way to do it. It would afford itself an economy of mechanism compared to how we did it before. Yet another way to do it would be to essentially have a branch transition, whereby this branch going out here, or this going out would lead to a branch. This, in effect, would be a little bit clearer. It would make it clear that these are sort of mutually exclusive options based on some condition. And we have that going that way. Oh, what happened to my, oh, sorry. This one would go the other way. Part of this would, okay. So we would have another branch from this same guy going up from here to this, to at work. And this one here would be triggered at that time. It would need no age. This one would go to the workplace, and the condition for it would be that their age is greater than 18. So under this condition, they go this way, otherwise they go that way. And that would even, I would argue, be a little bit clearer in the sense that it would make it clear that the transition is triggered by the same thing, and then you either go this way or you go that way, depending on some condition. The condition here being based on age. Having done that, so if your age is greater than this, you go this way and you move to the workplace. If your age is less than 18, and in the other cases you move to your school. And all of these are triggered by this timeout from being at home. So having done that, you could run the model. First thing to do, build it, just make sure it's happy, run it, and we'll again see the behavior here, where people go between their homes in blue, their workplaces in red, and their schools in yellow. So what we've seen here is two basic lessons that I'd like you to take from this. The first is there was a subtle bug having to do with initialization of the agent. When you left this room for lunch, there was still a problem because this value here, we were attempting to find the closest school, and the position of this agent wasn't yet set, so it couldn't find the closest school to them. And by the time their position was set, the closest school was already determined, and it never re-examined that choice. Here, we now examine it at time of entry. We choose the closest school coming in here. And at time of entry, their position is set for sure. By the time you enter the state chart, it's fixed. So that's something to watch out for. I've seen that sort of bug once or twice before. Kurt, I think, has encountered it as well. And basically it has to do with which of these things get computed first, people's location or these variables. And to avoid that issue, to sidestep it, you can set things based on the entries to the state chart. That's point one. Point two is that when we have a state chart, when we have things to do in any logic, often there's more obvious ways, there's more transparent ways to do them, to undertake them, and more complex ways to undertake them, less transparent. And it bears a little bit of thinking to figure out what's the best way to represent this. And I would argue that this representation here is both logically more clear as to what's going on. So you're going either to work or to school. The code is easier to understand. If you're going to school, you move to your school. If you're going to your workplace, you move to your workplace. And in both cases, it's after 16 hours. I would argue that that's significantly easier to understand than that code we had there earlier. So just be aware that a given model often lends itself to expression in a huge diversity of ways, and there's an art to sort of cleaning it up over time. It's called refactoring. You change the model structure without actually modifying its behavior in any way. You keep it logically the same, functionally the same, but you improve its clarity, its transparency. And we do a fair bit of that in our work. And I just want to share that those principles can be applied to your good effect. So here we have this model. It's working with people going to the nearest school as desired, and I'll provide this to you on the Dropbox, so you can make use of it. Okay, so that was a little bit of recap over